Okay, welcome back to another video in TCX1004, and this week we're going to cover basic graph theory. So in this video, here's my game plan. We're going to cover why talk about graph theory. It's kind of a new thing. We're going to cover some basic terminology. We're going to talk about some special types of graphs, and then we're going to cover some theorems about graph theory. Also, towards the end of the video, I'm going to show you something called pigeonhole principle. It's something that I think I should have left up to in the previous week, but I also felt like it didn't really fit in neither here nor there. It's just a very useful principle that I wouldn't say deserves its own topic, but it is something that I think people should know. So towards the end of it, we'll just very briefly mention what the pigeonhole principle is. And the reason for this is because usually in combinatorics and graphs, they are actually the topic that's taught together. And typically in that fashion, pigeonhole principle is also covered. So it's kind of like a bit out of the way, but people do it, and I think we would be remiss to not do it either. So I'm also going to cover this towards the end of the video. Okay, so let's begin with why graph theory. So here's a question for you. Let's say that you wanted to route yourself from, you want to find your way home through the MRT station, for example, something along those lines. How do you do this? Well, one way might be that to figure it out, you want to figure out what's the best way, you might use Google Maps. If let's say you're trying to discover a new path, how does Google Maps know? Right? So Google Maps can tell you, take this train, take that train, take the green line, then take the red line. How does Google know? How does their computer figure it out? Right? In a very similar vein, computer games, for example, in computer games, when we do play games, I'm not sure if you do, but there is this whole idea of moving your character around. So you can click on a spot, for example, and your character moves. How does your computer know how to move the character and how to get it to where it needs to go? Right? So how does your game know the path? How do computers figure this out? Right? Along the same lines of how computers figure things out, let's say that you wanted to route your packets. So you're trying to watch a video. Let's say it's again, like for example, this lecture might be on YouTube for you. It might be on Panopto. When you make the request, when you click on the link and say, hey, I want the links to the video, or I want the contents of the video, how does your computer figure it out? How does your network figure it out? Right? So you click on something, some network packets get sent. How do those packets know where to go? When you want to go to Google, when you want to go to the Google website, the physical server is somewhere in the US, or maybe let's say one of the content distribution network nodes is somewhere in Singapore, but we don't physically know where it is, but the packet has to somehow make its way physically to the location. How does it know how to do that? Right? So these kind of questions are basically sort of the starting point for graph theory. We like to model these kind of problems that we want to solve, these kind of pathfinding problems, or these kind of, well, there's many kinds of problems. There's like shortest path problems, there's like minimum, connection kind of problems and stuff like that. Network bottleneck problems and the such. All of these are basically part of, the starting point would be to know what graph theory is. Okay. Along those lines as well, a slightly different thing is understanding data structures, right? So eventually when you guys learn data structures and algorithms, at some point you're going to have to talk about trees, or you're going to talk about different and interesting ways to create data structures. And for you to be able to do this, you would need to know some amount of graph theory, right? So understanding combinatorics for graphs is also super important. Okay, so sort of in summary of why we want to learn graph theory, right? Like really the biggest reason why I would say is that it's used to model problems in computer science, right? So you want to do any sort of like routing, you want to do any sort of pathfinding, you want to do any sort of resource allocation, you want to do some sort of, let's say for example, data flow problem, right? There's many instances of this where really what you want to do is make a graph out of it first. Right? And then your algorithms, your computer works on top of the graphs that you've made, right? So in TCX1004, right, our goal is to teach you to understand what graphs are, so that later on you can use them and you can understand like, what's all these graph algorithms and everything. Okay, so now that we've gotten that out of the way, let's talk about some basic terminology. So we're going to say that a graph G is actually a pair of sets. So it's actually two sets, V and E, okay? And V here is actually going to be our set of nodes and vertices. Set of nodes or vertices. So the name is a bit interchangeable. You can call it a node, you can call it a vertex. That's, either way is fine. And the second set is basically the set of edges. Okay, so an edge, to be clear, is a pair of vertices. I'll show you an example in a little bit. Okay, but so since E is a set of edges, you can think of E as a subset of V times V. Okay, one more thing to take note. we're going to say that a graph H is a subgraph of G, right? If basically H only takes nodes from V and only takes edges from E, right? So think of a subgraph as sort of an intuitive way of saying subset. Okay, so that was all very mathematical, and hopefully, you know, like for example, I could, if I wanted to be very mathematical, I could say, okay, here's a vertex set A, B, C, D, and then, you know, like I could say, I know the edges are supposed to be pairs of vertices, right? So for example, we can make E to be a set of pairs here, A, B, D, A, C, C, A, D. But I would argue that this is very unintuitive. Almost no one really writes it this way, right? In fact, most of us do things very pictorially. So for example, we know that I have 4 nodes here, A, B, C, and D. So I'm just going to put 4 nodes on the screen. So A, B, C, and D, right? So these nodes here, you can call them vertices as well, are basically, you know, pictorially what you would draw. Typically, we would draw them as just circles, and we would give them labels. Okay, what about the edges? So we know that A is connected to B, we know that D is connected to A, we know C is connected to C, and A is connected to D. So if I wanted to draw the edges, one way to draw it would be like this, right? So basically lines between the nodes are what connect the edges. Okay, so really this is all there is to graph theory in terms of a definition. It's really just you have a set of items and you have a way that they are connected. It sounds kind of like relations if you think about it, where V is the set of objects and E is sort of the relation, and they kind of do share that common factor, right? But in graph theory, when we made this, we kind of wanted to focus on special kinds of graphs and not just arbitrary relations. Okay, so in particular, there are actually 4 kinds of graphs at minimum. There's actually more, but there's 4 kinds of graphs at minimum that we care about. And right now, so there will be like undirected graphs, there'll be directed graphs, there'll be simple graphs, and there are multi-graphs. Not multiple graphs, sorry, multi-graphs. Okay, so let me show you what I mean, right? Today's video is really all about showing you examples. Okay, so an undirected graph, let's just constantly use the idea of these 4 objects, right? So A, B, C, and D. Okay, so these 4 nodes that we have, an undirected graph is a graph where the edges have no direction. Okay, so when I say no direction, what I mean by this is that if I know A is connected to B, it must be the case that B is also connected to A. Okay, so intuitively you can think of this as being symmetric if you want to, right? So for example, A is connected to D, we also know this means D is connected to A, this is implicit, and if C is connected to C, that's it, right? So intuitively speaking, the edges in an undirected graph have no direction. Okay, so the connection is two-way, basically, right? So usually when we draw this, we omit the arrowheads. In other words, when we draw it, we just draw straight lines, we don't draw arrowheads. This is for an undirected graph. So if you ever see a graph that looks like this, you know it's undirected. You know it means that A can go to B and B can go to A. Okay, and to be clear, for this graph, A can't go to C, D can't go to C, B can't go to C. I hope this is pictorially clear. Okay, so that was an undirected graph, and really that's all there is to it, right? What about a directed graph? Okay, so a directed graph is when now the edges have directions. Surprise, surprise, it's in the name, right? So for example, now my edge set, if I set A to B, right? So for example, I have the pair A to B here. It does mean that A can go to B, but it does not mean that B can go to A, right? So if you still want to represent a two-way connection, you need to actually include both of the edges, right? So for example, A can go to D, so there is a pair there, and D can go to A, so there's a pair there as well, right? So edges in a directed graph have a direction, right? So think of the directed indirected graph as saying there is a direction. Okay, so so like I mentioned, node A can go to B, can go to B, but not the other way around. This is something that's important to take note for directed graphs, right? So this time around, when we draw it, we actually do include the arrowheads. We don't want to omit them, right? This is a sign to everyone that the graph is directed. Okay, so that was direction. Now, what about the concept of simple versus multi-graphs? Okay, so simple graphs have no self-loops, okay, and they have no duplicate edges. Okay, so in other words, a simple graph can be directed, it can be undirected, okay? So simple graphs can be directed, that's fine. They can also be undirected, this is also fine, right? But no self-loops, okay, those aren't allowed, and something called parallel edges, which I'll show in a bit, are also not allowed, right? So those are simple graphs. Let's move on to multigraphs. Okay, so a multigraph can have self-loops. This is completely fine. Or you can have something called duplicate edges. Okay, so a duplicate edge is, for example, if you pay attention to the A and B nodes, they have two edges between them now. Think of a multigraph as basically saying that you can have multiple edges between any pair of nodes. Okay, so we've covered four things here, right? So in summary, a graph can either be directed and simple, or it could be undirected and simple. That's also possible. Or it could be directed, a directed multigraph. That's also possible. Or it could be an undirected multigraph. This is also possible. Okay, so these are the four kind of graphs that we have. When should you use them? It depends on your scenario, right? So for example, let's say that you're traveling on the highway. You know that, for example, during rush hour, driving home is going to take longer than driving towards work, probably, right? Or you can imagine how, for example, on the MRT line, when you take Clementi Station and let's say you're headed towards the city, maybe that's less crowded than, you know, heading from the city back home in the evening because of the amount of traffic, right? So depending on the kind of scenario you're in, right, depending on the relationships you want to model, the graph is either directed or undirected, right? What if there's multiple connections between, let's say, Clementi and Commonwealth? Like there's many buses, there's many trains, right? So there are many ways that these two things are connected. Maybe you should use a multigraph instead, right? Okay, so that basically roughly summarizes the terminology for the four different kinds of graphs. And now we need to talk about different terminologies for the features of graphs. Okay, so let's start with degree first. What is the degree of a node? Again, today is really all just about vocabulary, all about introducing you like you know, new words. Not a lot of theorems going on today. Okay, so what is the degree? Okay, so let's go back to this example of a graph. This is a undirected multigraph. Okay, so in this undirected multigraph, okay, what is the degree of a node? The degree of a node is the number of times the vertex V is an endpoint of an edge. Okay, so what do I mean by endpoint of an edge? Here's some intuition. Okay, the degree of some node A, okay, is the number of edges that are connecting A. Okay, so if you look at our edge set E, you might notice that A appears in the edge set 3 times, right? So the degree of A is 3. Okay. Okay. What about C? Well, node C actually appears in the edge set twice. It might be tempting to think once, but C is an endpoint 2 times, right? Because of that single edge that starts from itself and points to itself. Okay, so for an undirected graph, the degree of a node is basically just the number of times it's an endpoint of an edge. So what about for a directed graph, right? So for a directed graph, right, we use an in degree instead. So the in degree counts the number of edges coming into V. So for example, the number of the in degree of A is 1 because there's only one edge coming into node A. Okay, the degree of B is also 1 because there's only one edge coming into node B. Okay, the degree of C is also 1 because there's only one edge coming into C, and so on. Right? So similarly to an in degree, there is a notion of an out degree. So what is an out degree? It's the number of edges leaving or going out from node V. Right? So degree for the out degree of node A is 2 because there's 2 edges leaving A. And I think you can see, but like for example, the out degree of B is 1, there's only one edge leaving. The out degree of C is also 1 because there's only one edge leaving. Okay, so that's the notion of degree. There's degree, there's in degree, and there's out degree, right? Okay, so moving on, more terminology. What is a path? So a path is a sequence of vertices that are connected by edges, and here the vertices do not repeat, right? So think of it this way, right? A path is really you just trying to walk the graph. Okay, so for example, let's say I start from C, right? I can walk to node D, using some edge. Okay, I can walk from D to A using some edge, and then I can walk from A to B using some edge. Okay, now take note here that in the path we don't repeat vertices, so we will never revisit vertices. Okay, so this is the definition of a path of a graph, right? So think of it this way. You know how we talk about path finding on a graph? It's basically us trying to say, okay, you know, I have some, you know, MRT station, I have some computer network, like internet network. How do I, you know, find my way from one point to another, right? Path finding is when we're basically just trying to find a way via our connections to go from point A to point B. Okay, moving on, let's talk about the notion of connected. So two nodes are going to be connected if there exists a path between them, right? So for example, I hope it's clear from the picture here, but nodes A, B, C, and D are all connected. There's definitely a path between any of them. For example, B is connected to A, we know that. We know B is connected to C because it can go through A. It could also go to D if it wants to, right? A can go to D, A can go to C, so on and so forth, right? So they're all connected. On the other hand, E is not connected to any of the other nodes, right? So connected really just means look at the graph. Is there a way for you to only take the edges to go from one node to another, right? Hopefully this is very intuitive. Okay. Moving on, what's the notion of a connected component? So a connected component is a maximal set of vertices such that all of the vertices in the set are connected to each other. Okay. So for example here, I have that A, B, C, and D are in a connected component. Okay. So the reason why they are a connected component is because, think of it this way, it's a set that contains as many vertices as possible, okay, so that they are all still connected, they can all reach each other. On the other hand, if I said A, C, and D only, these do not form a connected component because it is not maximal. Okay, in other words, why is it not maximal? Because we should have included node B as well. Okay. What about A, C, D, and E? Well, now this does not form a connected component because we can always find a pair of nodes that are not connected. So for example, A and E are not connected, right? No matter how hard we try, there's no way for you to go from A to E or the other way around. Okay, so this is what we call a connected component. Think of a component as a subgraph that is as big as possible, where every node, you know, in your subgraph can reach each other. Okay, so what about a cycle? Hopefully these names are very intuitive, right? So a cycle is a sequence of vertices that are connected by edges, and only the first and last vertex repeat. Okay, so for example, C can go to D, D can go to A, and A can go to C, so now this is a cycle. Okay, so again, I stress only the first and last vertex must repeat. Okay, also one more thing to take note, a cycle must involve a minimum of 3 nodes. So we can't say A to B, B to A is a cycle, because cycles have a minimum size of 3 nodes, right? So C, D, A is fine because we involved 3 nodes when finding our cycle. Okay, so to summarize a little bit, we've basically done degrees, we've basically done components, we've done connectedness, we've done paths, right? So you know, those are the kinds of terminology that we're going to use. Okay, and now let's focus on 3 types of special graphs. Okay, now these graphs very commonly show up in CS, in most places in CS. It's true that other graphs also do show up, but these 3 are sort of the special cases that we like to think about. Okay, so let's begin with trees. So trees are graphs. Again, a graph is a pair of sets, V and E. Okay, so what's so special about trees? Well, first of all, they're connected. So in other words, all nodes can reach each other. Okay, and it has exactly V minus 1 edges. In other words, the number of edges we have is exactly the number of nodes minus 1. Okay, so that was a lot of text. Let me show you what the visual intuition looks like. It basically looks like this. We have a graph where if you count the number of nodes and you count the number of edges, you'll realize that the number of edges is basically the number of nodes minus 1. Okay, and not only that, but basically what has happened here is that all of the nodes are reachable from each other. So this forms the entire graph is one big connected component. Okay, so this is what a tree is. It's basically a graph that is where there are no cycles and every node is connected. Okay, so trees have a special form where we might want to make a root out of it. So this is called a rooted tree. It's when not only do I give you a tree, I also tell you what the root is. And typically in computer science, our roots are at the top of the tree. So everything is upside down. Okay, so in this case, B here is we're gonna, for example, let's say this is my tree. I'm gonna say that B here is my root. Okay, so here are a few more bits of terminology. When we move down from the root, when we move away from the root, okay, we can think of, we can look at each node and look at it as a child. So for example, since we're moving away from the root node B, okay, we're gonna say that F is a child of B. Okay, we can also say that B is the parent of F. Okay, so very similarly, I can actually say that D is the child of E. I can say that E is the parent of D. Okay, so with that terminology in mind, right, since the root is at the top of the tree, you can imagine how the leaves must be at the bottom of the tree. Okay, so leaves are basically nodes that we're going to say have no children. So think of these as the ones that are all the way at the bottom, or all the way the furthest nodes away from the root. Okay, so what about the nodes in between? Well, the nodes in between are what we call internal nodes, and internal nodes have children. Okay, so as long as the node has a child, it's called an internal children. So you can also think of it this way: if you're a parent node, you're an internal node. Okay, so a few more things to cover. What about the height of a tree? Again, I really hope all of this terminology is very intuitive. So what about the height of a tree? Well, the height of a tree, mathematically speaking, is just the longest path from a root to a leaf. Okay, so in this example that I have here on the screen for you, the height of the tree is going to be 2. Okay, so why is it 2? Because the longest path that we're going to take could either be BAC or BAF or BED. Right, so we took 2 edges, so the height is 2. Right, now I'm going to say one thing, which is that sometimes it's part of convention where people count the nodes rather than the edges, so they might disagree with you or with me and say that the height of the tree should be 3 instead. There is no standard convention for what the height of a tree is. It's one of those things where we decide when we, usually one of us will be off by 1, basically. Right, so just bear that in mind, that sometimes some people might look at a single node and say, oh, height 0. Some people might look at a single node and say height 1. That's possible. Some people might look at this tree and tell me, hey, the height should be 3. Right, that's completely possible. Okay, so just bear in mind that this definition is a little bit subjective, right? So people might disagree with you on whether we should start counting from 0 or whether we should start counting from 1. Okay, moving on. A k-ary tree. So a k-ary tree, okay, is a tree where every node has less than or equals to k children. Right? So in this example I've shown you, right, you can see how some internal node, all the leaves have 0 children, right? We have an internal node here that has 1 child, we have an internal node here that has 2 children, but really the root node has 3 children, right? So the maximum number of children we have here is 3. So this is actually a 3-ary tree, right? It doesn't matter if it's the root node or an internal node, as long as some node has 3 children, we're going to call it a 3-ary tree. If, for example, I put more nodes in here and there were 4 nodes, some parent that has 4 children, then this would have been a 4-ary tree, right? You can call a 3-ary tree a ternary tree, right? So if it only had 2 children, we could call it a binary tree. Yeah. Okay, so moving on away from trees, which are very simple types of graphs, there are also bipartite graphs. Okay, so a graph G is bipartite if we can partition the set of vertices into 2 sets A and B, so that there are no edges among the vertices in set A and there are no edges among the vertices in set B. Okay, so those were a lot of words. What does this mean pictorially? Well, basically, here's an example. I have, let's say, 5 nodes again. Right, this time around I've arranged A, B, C, and D in a cycle, and E is all by itself. And one question you might want to think about is whether the graph is bipartite. In fact, I kind of would encourage you to pause the video at this point and maybe think to yourself, can you divide can you know, the set of nodes here into two sets so that there are no edges among the left set and no edges among the right set. I'm going to assume you paused, or maybe you didn't and you just want to see the solution. But here's the solution. So we're going to rearrange the nodes this way. Okay, so here are the two sets for you. And think of it this way: AD is on one side and BEC is on the other side, and the only edges that we see are all the crossing edges. There are never edges within the sets themselves. Okay, so for example, there are no edges among A and D, right? There are also no edges among B, E, and C. Okay, now this solution is not unique. Here is another viable way to show this, right? So instead of putting E on the right side, you could have put E on the left side. This still satisfies the condition the exact same way. Okay, so let's try one more example. What about this graph? Right, so now I have 5 nodes again, you know, but they're all in a cycle now. Okay, so you might want to pause the video and try to see that whether you can make a bipartite graph out of this. It might be a bit interesting. Okay, I'm going to assume either you paused or you didn't try, but either way, here's the solution, right? So no matter how hard we try, we can't actually make a bipartite graph. Okay, so for example, if I put A and D on the left set and I put B and C on the right set, you can see how F, it doesn't matter where we put F, it's going to cause an edge to happen somewhere, right? Okay, so maybe we made the wrong choice. Maybe we should have put F on the side instead. So let's put F on the side and let's put B in the middle. Now notice that no matter where I put B, again the same story applies, right? If I put B on the left set, then there's going to be an edge between B and D. If I put B on the right set, there's going to be an edge between F and B, right? So it really doesn't matter what we try, this issue is going to persist basically. So why is this the case? Here's the intuition. Okay, so no matter how hard we try, we can't make a bipartite graph, okay, if it has at least one odd length cycle. So I'm going to say that again: if the graph has at least one odd length cycle, it cannot be bipartite, right? So this graph, if you realize, is a cycle of length 5. It has 5 nodes in it, so it's odd length, okay? And because of that reason, it can't be bipartite. Okay, so that was bipartite graphs. Let's do one more, a complete graph. Okay, so a complete graph, hopefully this is the most intuitive actually. A complete graph is when every pair of nodes is connected by an edge. Okay, so give me any 2 pairs of nodes, there is an edge that connects them. Okay, so here's an example of a graph with 4 nodes. Again, you know, slow down the video if you have to. Notice here that A is connected to B, is connected to C, is connected to D, right? B is also connected to A, C, and D. C is connected to A, B, and D. D is connected to C, A, and B, right? So everyone is connected to each other. And you can imagine how, if you wanted more nodes, for example 5 nodes, then this is what it looks like. And again, pay special attention to how everything is connected to each other. Okay, so those are complete graphs, right? So hopefully beyond this point, eventually in the future, when you know, we start talking about networks, when we start talking about graphs and stuff like that, and we say, oh, you know, consider a complete graph or consider a tree, right? Hopefully this all makes sense to you. Okay, so a little bit enough on the terminology. Let's start talking about some theorems instead. So I have 3 theorems prepared to show you today, and these are in my opinion, the most important theorems that we have for graph theory, for computer science, right? There's actually a lot of theorems out there for graph theory, and this thing can get very deep, right? But these 3, in my opinion, are the best value for money, the best bang for buck, because these are the ones that most people would use almost immediately in computer science. Okay, so let's begin with the handshake lemma. Okay, so here's the statement. Given an undirected graph, again, a graph has 2 sets, V and E. Okay, we want to show that it holds that if I were to add up the degrees, it's 2 times E. Okay, so in other words, go through every node, and if you add up the degrees, it's somehow 2 times the number of edges, which sounds very weird. So let's see this in action. Here's an example. Okay, so I have a graph here. It has A, B, C, D, E. It has 5 nodes, and it has how many edges? 1, 2, 3, and 4. 4 edges. Okay, so we kind of expect 4 like that means we want to sum up the degrees, and it should be 8, right? So let's try doing this. So to sum up the degrees, I have to add the degree of A to the degree of B to the degree of C, D, and so on and so forth, right? So the degree of A is 2, the degree of C is 2, the degree of B is 3, the degree of D is 1, and the degree of E is 0. Okay, so the degree of A is 2, B is 3, C is 2, D is 1, E is 0. Okay, now if you whip out your calculator, you might realize that this sum actually adds up to 8. Okay, but hey, 8 actually is 2 times 4, so it's actually 2 times the number of edges, which might be a bit surprising, right? So why is this true? Okay, so here's an idea. Okay, so every edge, okay, connects two vertices, let's say U and V. The idea is that every edge that comes into the graph adds 1 degree to U and 1 degree to V, right? Since we're summing up the degrees of all of the nodes, right, we're always adding 2 to the entire sum, right? So every node adds 2. So, sorry, every edge adds 2. Since we have, the size of set E number of edges, 2 times the number of edges is basically the correct sum, right? So this is the handshake lemma. The proof is very, well, if we are not being rigorous, the proof is very simple, right? And this is a super useful result. Like, if you take an algorithms course, we use this a lot. Okay, let's move on to another one, which is also useful in an algorithms course: the size of a tree versus the height of a tree. Okay, so we claim that the given a graph G, again, a rooted tree, because we need the notion of a height. For you to have a notion of a height, the tree must be rooted. Okay, if the tree has height h and it is k-ary, in other words, it has k children, right? Then the minimum number of nodes it has is h plus 1. Okay, the maximum number of nodes it has is k to the power of h plus 1 minus 1 divided by k minus 1. How do we see this? Here's an idea for you. Let me show an example. So let's revisit the tree that has height equals to 2, and it has this tree is 3-ary. Right? So let's do an example of 3-ary trees. So if I promise you that every node in the tree has at most 3 children, okay, well then the minimum number of nodes has to be only the nodes from the root to the leaf itself. So we create a quote-unquote straight line graph, right? So this is a straight line, and the idea is that basically, if you think about it, this is a tree. There is no cycles, right? Every node is connected to each other, so this is definitely a tree. The height of the tree is 2, right? And this is the minimum number of nodes possible, because if I were to have any fewer, either the height of the tree is less, right, is lower, or the tree is not connected, right? So this is the minimum number of nodes from the root to the leaf. Okay, so what about the maximum? Here's the idea. To hit the maximum, we're going to make sure that every node has exactly the number of children it's supposed to have, right? So for a ternary tree, a 3-ary tree, we're going to force it so that every node has 3 children each, except for the leaves, which don't have any children. Okay, so for example, the root node we're going to say has 3 children, A, C, and D. If we wanted one more level of this, okay, what we're going to say is that, okay, so one thing to take note here, right, before I mention that, I almost forgot to mention this, but at the very first, the highest level, there's only one root node, right, one node which is the root. Okay, so at level 0, there's only one node, right? Notice how at the first level, let's say at level 1, so at level 0 there's one node, and at level 1 there were 3 nodes, right? Why? Because it's 3 times the parent, right? So however many nodes we had the previous level, we had to multiply by 3. So you can imagine how at level 2, the amount of nodes that we're going to have is going to be 3 times the previous level, which happens to be 3, right? Because every node at level 1 now has 3 children, right? So you have 3 times 3 nodes at level 2. Okay, so you can imagine how at this point, if we were to keep doing this, right, at level 3, we're going to have 9 times 3 nodes at level 3, right? We're going to have 3 to the power of I nodes at level I. Okay, but we wanted to count the total number of nodes in the tree. Okay, So how do we do this? Well, we just have to sum up all of the nodes at each level, right? So I had 3 to the power of 0 nodes at level 0. I had 3 to the power of 1 nodes at level 1. I had 3 to the power of 2 nodes at level 2, and so on and so forth. So to sum them all up, I am basically just going to write this in a summation, 3 to the power of I from 0 to h, where h is the height of the tree. Okay, so if you remember what this resolves to, which I hope you do, this is geometric progression, so this resolves to 3 to the power of h plus 1 minus 1 divided by 3 minus 1. Okay, so let's take our equation out for a spin, right? So coming back to this tree, whose height is 2, right? You can manually count it if you want to. You should see 13 nodes, right? So let's see if the equation works, right? So my tree right now on the screen has height 2, right? So for example, BAX has path length 2. Okay, so how does this work? Well, if you plug into the equation, 3 to the power of 2 plus 1 is 3 to the power of 3, which is 27. If you minus 1, divide by 2, okay, which should give you 26 divided by 2, which happens to be 13. Right, and indeed, I'm pretty sure if we do count the nodes, we would realize that the number of nodes that we have here is 13. Okay, so what about in general? Because we've done this for a ternary tree, but what about in general for other trees, right? So in general, for a k-ary tree, instead of putting 3 to the power of I everywhere, we can swap this out to be k to the power of I. And then the formula becomes k to the power of h plus 1 minus 1 divided by k minus 1. Okay, so that's a theorem counting the number of nodes in a tree versus the height of the tree. That's also very useful for algorithmic analysis, right? And the very last one, so the size of a complete graph, right? So the statement goes like this: given a graph G, again of a pair of nodes, a pair of sets V and E, that is complete, right? Then the number of edges E happens to be the size of V, choose 2. Right? Or we can see this as v times v minus 1 divided by 2. Both ways are possible. Okay, so there are 2 ways to prove this actually, this fact. We can do it combinatorially using last week's techniques, or we can even use what we learned today, actually. Okay, so let me show you how to do it both ways. Right, so given a set of v nodes, right, let's say there are n of them, so I'm gonna label them 1 to n, so v1, v2 until vn, right? So every possible way to choose a pair of nodes forms an edge, right? Because any pair of nodes has an edge between them. That's the point of being complete. So how many ways are there to choose a pair of nodes, right? So we've been through this. This happens to just be n choose 2 ways, right? Which actually proves what we want to prove. Now, there is a cooler way, in my opinion, based on what we learned today. And so let me use this as an example, right? So I have a 5-node complete graph here, okay? Now, notice here that if I have 5 nodes in my graph, right, the degree of any node is the same. The degree of every node is 4, okay? Why? Because it's connected to 4 other nodes. You can imagine how, in general, for a n node graph that is complete, it's connected to n minus 1 other neighbors, right? Okay, so let's use the handshake lemma, right? So the handshake lemma again says that 2 times E is the sum of degrees. Okay, if we know that the degree of every node is V minus 1, okay, how many times are we summing up this value? There are V nodes, so we're summing up V times. So this is V times V minus 1. And then if you just shift the 2 over, this becomes E is equals to V times V minus 1 divided by 2. But hey, that's also just V choose 2. Okay, so this actually summarizes what we should cover for graph theory, right? This is basic graph theory. There are some very useful facts here, like some useful theorems about graphs here, right? And hopefully you get accustomed to the terminology, right? So even though we won't actually be expanding on graph theoretical concepts in TCX1004, it's something that you're going to see is pretty useful in algorithms. And I think you might see it being useful in AI, but I don't know how much of that they will cover. But turning problems into graphs and then using your building solutions on top of that this is the very first starting point. Okay, so I said I would end the video on something called the pigeonhole principle. Again, it's a bit of a mishmash of a topic, but it felt like it wasn't going to fit anywhere, actually. So the last thing I want to talk about is the pigeonhole principle. Okay, so again, no more graphs, but here's an idea. If I'm given n pigeons and m pigeonholes, okay, think of it this way: the pigeons want to go into the pigeonholes, right? We're gonna claim that there exists a pigeonhole, at least one, not all of them, exist at least one that has at least n over m ceiling pigeons. Okay, so for example, if I had 4 pigeons in my example here, I have 3 pigeonholes. Okay, because the pigeons want to find a home, want to nest somewhere. Okay, I'm gonna claim that there exists at least 1 pigeonhole with 2 pigeons. So 2 pigeons have to share a pigeonhole here, right? So how do I see this? Think of it this way, right? The best that we could do is that each pigeon first, each of the 3 pigeons first finds a home, a place to nest, right? But the final pigeon, right, needs to find somewhere to go, right? So it could either have tried the first pigeonhole, the second pigeonhole, nope, the third pigeonhole. Regardless of where it goes, it always needs to share the pigeon, right? And if you think about it, 4 divided by 3 ceiling is 1.33, 1.333, ceiling of that is 2. Okay, so here's an example of how you might want to use this proof, right? So for example, we can make something like the following claim: there are at least 2 people in Singapore that have the same amount of hair on their head, right? How do we prove this? It sounds kind of weird. So here's the idea, right? Singapore's population 2 years ago, I think was recorded at around 6 million. Okay, and if you look this up, on average, a person has around 100,000 hairs on their head. Okay, so it stands to reason that if 100,000 hairs on their head is the amount that someone has, it's very unlikely to have more than 1 million strands of hair on someone's head, right? Because we don't want average, we want the maximum, right? So think of it this way, right? If we treat people as pigeons, right? And we're gonna send them to a pigeonhole. Okay, so which pigeonhole do we send them to? Think of it this way: we're gonna count someone's hair. And if let's say they have 5 strands of hair, they go to the pigeonhole that has number 5. If you have 1,000 strands of hair, you go to the pigeonhole that has number 1,000. Okay, so think of it this way: because there are 6 million people, and let's say that 1 million is in an upper bound on the number of strands of hair that you can have, right? There must be at least 2 people that went to the same pigeonhole. And the reason why they went to the same pigeonhole is because they had the same amount of hair on their head, right? So this is how the pigeonhole principle works. It's hopefully quite obvious, but it's a very common technique that should be mentioned, right? So it's something that, again, didn't really feel like it fit anywhere, but it's still really much worth mentioning. Okay, so this summarizes the topics that we have for you today, and in the next week, we'll basically finish off with basic probability and statistics. Okay, see you next week.